So one of the things I was doing just in preparation for this talk was actually listening to Magnus's talk, and I was kind of worried really that some of the terms and descriptions and things that he was using was things that I'd invented 12 years previously, and it's kind of weird to see those words kind of come back at you, and things like base backup, like I'm glad that description still kind of has meaning. If I'd have called it something completely different, then that would have been a bit weird. Just with that in mind, what I'm going to talk about here is the current set of thoughts and architectures and code that we've been working on. So what I want to do is try to put some context around the idea of big data, and specifically big data with PostgreSQL. Now, while I was writing this talk, I sort of became aware that actually I could really run this as a 3-day course because there's kind of enough detail about why this and why that and what are we doing about this and how quick is it to do that. And obviously I've got 50 minutes to discuss this. So what I'm aware of is I'm going to cover the things I'm thinking about, and that might not be the things that you're thinking about. Okay, so give me some room with the topics that I'm discussing. The first thing that is important to me is to understand what big data is for. That's a much better question than just saying what is big data. And for me, big data is trying to summarize the idea that you need detailed data in order to do full and complete analytics. And detailed data, in a lot of cases, leads to very high volumes of data, and thus comes the phrase big data. And if you look back in time historically, the whole study of statistics started with sampling methods, and the SAS methodology for statistical analysis, the first word in their methodology used to be sample, as if that sampling was the be-all and end-all of statistics. And over time, we've realized that actually sampling isn't necessarily the be-all and end-all. It's actually more about looking at the detailed data. And what's also happened over time is that our ability to trap detailed data has increased. If you look at back 20 or 30 years, the transaction rate that you could get on a mainframe was something like 200 transactions per second. So the idea that you would be able to collect big data in the way that we know it today was just simply not possible. So CPU rates have increased, technology's increased to the point where we can actually trap very significant data volumes and use that for analytical purposes. Now, why would we care about big data in the context of PostgreSQL? Because many of you will realize that Postgres is at its heart a transactional system, and what the hell has that got to do with big data? Well, actually, what I wanted to do was give you a viewpoint, a sort of high-level overview of how all these systems fit together in most enterprises. And what we see is we have front-end transactional systems that are doing the basic data collection, and then that generally feeds through into what used to be called an operational data store, but is sometimes referred to as a data lake these days. And then from there through to an analytical system. And as a result of this spreading out the data across multiple systems, it allows you to use a specialist transactional technology, which is typically how people think of PostgreSQL, and at the same time use specialist analytical technologies, and people are kind of fixated with the thought that that means Hadoop now, okay, but that, that itself has changed over time. And then there's actually, if you look, there's actually a backfeed on my diagram here, and I like laser pointers, so I'll just spend time pointing at that. The idea of the backfeed is that this then creates what we call a closed loop system, in the sense that data is being generated on the front end, and then analytical results are feeding back to the front end to allow us to assess what should happen on the front end. And a typical example of this might be some kind of financial card application with a fraud analytics system. So the analytical system is used to assess what types of frauds are going on, and then we decide how to spot that type of fraud, and then a filter mechanism or some kind of information gets fed back to the front end system so that we're able to highlight frauds in progress within, say, 10 or 20 milliseconds, whereas that is clearly not going to happen in the sense of a transaction happening, an analyst kind of running 5 queries on it to see if it's safe and then passing it. That type of transaction system needs a response within 10 or 20 milliseconds in order for a viable financial company to run. So there needs to be a feedback to the transactional system. Now, my interest in this type of diagram is in saying if the transactional system is the source of the data and the place where you execute the rules that you gained from your analytics, why do you not also calculate your analytics on the front end as well? And actually, if you do that, then you can circumvent the whole data flow and actually just have a single set of systems. That's one viewpoint. Another viewpoint is also to say, why don't we use Postgres for all of these systems? Why complicate matters by having Elasticsearch and 17 different server types all kind of glued together with bubblegum to make these things work? So this whole flow is going to be a lot easier if we're using a consistent, easy-to-use technology. And what I'm trying to do is put together an architecture that means that all of this can be done with Postgres technology, okay? Those are my goals, to allow people to fully exploit Postgres for all of the things it's good at, not just its ability to do transactions. So what I'd like to do now is kind of go on a bit of a journey, going through different thoughts about how these types of systems work, and really just to start from a list of the limits that we have with PostgreSQL. You can see maximum data size unlimited, maximum table size 32 terabytes. Now, depending on your viewpoint, that 32 terabytes is either quite small or quite large. Now, how many people have got more than 32 terabytes of data? Well, I don't know. I mean, however you want, however you add it up. Anyway, so the basics there is for us to support larger Postgres databases, we're going to need to do something because that's a current physical limit of the system. And that's one of the reasons why some people have been looking at Postgres partitioning, and that's also why Alvaro Herrera has been looking at doing a storage plugin because that would allow us to do things like vertical partitioning as well. So generally, horizontal or vertical partitioning is one way that we can exceed that 32 terabyte barrier. So part of the Columnstore project that we've been pursuing for the last couple of years would be to exceed that limit by putting one column per table, and that then would give you a limit of 32 terabytes per column rather than per table, which would basically give you a sort of 10 to 100 times increase on those limits. Now, some people might say, well, let's look at the use case, because if you've got a Postgres database with 30 terabytes of data in it, then you're probably not going to be doing too much complexity in that kind of system if it's running on a single node. And that's absolutely right. So there are systems that big, but they tend to be of the form where the system's actually more akin to a data bucket, in that there's a lot of data going in and not a lot of data coming out. But as soon as you start to do various types of use case, for example, analytical complex queries, then the actual size of Postgres database that you can cope with quickly comes down. And that's when we start to need to look at more advanced technologies, and that's why people have been working on parallel query, which, as you'll have learnt, is soon to be released in 9.6. Now, that's actually something that we've been working on for more than 5 years. If you look at the minutes of the developers meeting back quite a long time, you can see that we took various decisions about how that would work. We invented things called background workers that would be the basis for how parallel query works. In 9.1, for example, we introduced things called shared snapshots. So actually the basics of that technology have been brewing for a very long time. So I'm very pleased to say that that's coming out now in 9.6, but that's not the end of it, as we'll see. So there's various other use cases to discuss, but I just wanted to start by looking at the analytical use cases. When you use something like Hadoop, you will be familiar with the idea that you're basically analyzing a single big table full of detailed data. And actually that requires you to then prepare the data ahead of time. The original systems that were used as data warehouse systems, things like Teradata, took the approach that you would want to have a full third normal form database. And because that was basically the way that people thought about modeling 20 or 30 years ago. And then over time, people realized that actually if you simplify the model, then your queries go a hell of a lot faster. And that's where the star schema came from. So there's actually a kind of middle ground between a single table and the full third normal form. Now, the problem with this, when you look at what happens with Hadoop, is if you're basically doing all of your analytics in a system that can only cope with single tables, then that's pretty limiting in what you can achieve. It may work very well if you're the type of company that really does have petabytes of information, because you really do, in those cases, have to simplify it. But what I'm seeing out in the people I speak to is that that type of technology is being grievously oversold, and people are trying to use Hadoop on sort of 5 or 10 gigabytes of data and fighting against the fact that it contains quite a few restrictions. So actually what I'm seeing is that people are bouncing off Hadoop and coming back to Postgres and other relational systems. Now, not in all cases. There is a role for that type of technology, but it isn't in the type of realms of data analysis that most of us deal with. If you think about how many people there are in China and whether all of those people have mobile phones, it turns out that that's really not a particularly big database, even if you have 1.2 billion customers, that's still sort of tens or hundreds of gigabytes system, and that will fit on my laptop quite easily, which isn't really what people talk about when they think of big data. The other thing that I wanted to talk about was the type of use case where we have scalable rights. And you'll be familiar with a whole host of systems that advertise their ability to manage databases in a very elastic, scalable manner. Now, it doesn't matter what the names of those systems are. I'm sure you're familiar with the ones that I'm talking about. What I wanted to do there was just talk through some of the difficulties of managing data using those types of systems. So typically you will find that data in those systems is spread across multiple nodes using a hash distribution mechanism, and that is typically on a single column, whether it be an ID attribute in a JSON blob, or whether it actually be a specifically identified column in a relational table, depending on which systems you're talking about. Now, if you look at the way that those systems work, it looks really cool to be able to spread your data easily across multiple nodes. But if you look more carefully at the way that those things work, you can see the problems start to emerge. Because I think it probably goes without saying that people with relational experience are familiar with the idea that you may want to access a table by more than one key. And if you can only access the table by its primary key, that becomes extremely restrictive in the type of applications you can write. And the first thing that you actually want to invent when you use those systems is you want a secondary key against that data, whether it be something like a system where you have a customer number and their credit card number. And the customer, when they ring up, they never tell you their customer number, they only tell you their credit card number or their name. So how do you look them up on that kind of a system? So in fact, what happens is you need a secondary key to this data system, and that's where it starts to break down, because if we hash the secondary key in order to get fast lookups, then we end up with the lookup key is on a different node to the main primary key. And then all of a sudden, you need multi-node access to this data, and then suddenly you notice that you did need transactions after all, because it's a bit hard if you add data to the table and then you crash before you added the index to the data, and then nobody can find it and you get the wrong answer to the query, right? So actually it turns out that as soon as you have secondary access paths to data, you immediately need transactions that span multiple nodes. And so actually these very simple systems that appear to look like a very good way of scaling, actually things become a lot more difficult than you've been sold. So what I wanted to do is really highlight that, because I think some people are expecting Postgres to adopt a similar, dare I say, sort of NoSQL approach to sharding. And my hope is that we don't implement an extremely simple mechanism, because what's going to happen if we do is we're simply going to fall foul of exactly the same problems that those other systems have. And in typical Postgres form, we will admit to them, we'll worry and fret about them, and there'll be 300 blog posts saying, this is broken, how could we deliver this to our users, and that kind of thing. So actually what I hope is that we hold back on providing very simple technology in Postgres, and actually take the time to go the extra mile so that when we deliver a proper system that works multi-node in the same way that you would expect Postgres to work. So what I wanted to do now was explain some of the things that we've been working on in the context of that architecture that I showed you before. So this system here is the Postgres transactional system, and in this architecture we needed to transfer data from the front-end transactional system through to some back-end analytical systems. And it would be great if we had a data movement technology that allowed you to filter that by table, and it would be really cool if we were able to do things like send through inserts but not deletes, and it would be really cool if we could have triggers on the far end that would access transformational rules, and that is exactly what we get with PG Logical. It's a data movement engine that allows us to move data out of the transactional system, filter on database or table, and actually also filter on things like inserts and deletes. So that's actually already been built. So that's a good thing. Then if you're building a large scalable data store that speaks roughly Postgres, then you're going to want something that spans multiple nodes. And that's why for some time now we've been building the next generation based upon the Postgres Excel technology. And I'll talk a bit more about that in a minute. And then on the analytical side, we've also released something called Tudor, which contains a package called Orange. Tudor stands for Second Quadrant Unified Data Architecture. And the Orange package is actually a data mining tool that's been modified so that it generates SQL code. So it doesn't just access Postgres, the whole data flow engine within the data mining tool has been modified so that it actually generates quite complex SQL, and so it pushes the work from the data mining engine through onto the analytical database. So by generating SQL, this system is able to take advantage of the power that we get from the parallel processing systems. So there's no work needed to speed up the data mining. You just generate the SQL and it executes on the database. And then once you've built an analytical model, you would like to export that so that it executes back on the front-end system again. And again, that's what we've already built, something called PG Predict. It allows you to export a predictive model and export that back as a Python function to execute on the front-end systems. So your data mining system can build some kind of decision tree model or various other kinds of model and then export that for execution on the front end. Okay, so what I'm saying to you here is that we've actually built all of the pieces for this analytical architecture. Now, I'm not saying that, some people have already got these things in place and you've chosen other technologies. That's fine. What I'm saying is simply that we've gone to the trouble of building this complete architecture now to allow you to move from the transactional out into a full analytical architecture. Now, one of the things that people say to me is simply, can you give us a little demo of what Orange is like? So what I've got here is a very short video that gives you a better understanding of what you get with with orange. So I'll just play this. So it's only a short clip. I just wanted to stay silent during that so that you've got a chance to review what we're seeing. What you just saw is a mechanism by which you define the data flows from the database. You pull data back and then it will perform either visualizations or model building. Now, obviously what you just saw there was all visualization, but actually the way that it works is all of the different elements of these data flows. If you look on the left-hand side, you can see there are a number of components that deliver visualizations, but there's also components that deliver things like classification and regression. So it's actually not just a visualization environment, it's a full data mining environment. So just to emphasize the couple of things about this that are interesting and relevant is that when you build a complex data flow, it doesn't bring all of the data back and run on your PC. It generates SQL that gets fired against the main database engine. So the main task is actually executing on the database, not on the laptop, okay? That's the first point. The second thing is all of the visualization technology has been built completely around the data sample technology that we built into Postgres 9.5. So you're able to specify sampling mechanisms, for example, along the lines of where you say, I want a picture of what this data looks like, and I want it to happen in 2 seconds, even though I'm accessing a 30 terabyte table. And so Orange will actually bring back the data based upon that sample. So it's actually been heavily modified with Postgres in mind, okay? So, as a set of pretty pictures, I wouldn't bother showing it to you unless there's a reason, and the reason is it's tightly integrated with Postgres, okay? So what I wanted to do is just fly through some details about Postgres Excel. Many of you will have seen some of these this information before, but some of you it's new, so I wanted to take the time to go through that. So Postgres Excel is a version or a variant of Postgres. Some people would say, oh, it's a fork of Postgres. Well, the intention is not for it to be a permanent fork of Postgres. It's currently a modified version, and we're going to try our hardest to put the modifications back into Postgres. And so far, we've done that with all of the other things that we've been building, for example, BDR and logical replication, etc. It's open source and it follows the PostgreSQL license. So the architecture of Postgres Excel is that we have a number of coordinator nodes, and then below that we have a number of data nodes. So the data itself is actually spread out across the data nodes. So if we've got a very large table, then it will actually be spread across multiple systems, not just residing on a single system. Now, one of the big differences about this is that there's something called a global transaction manager, and that allows us to execute changes on multiple nodes while retaining the ability to have transactions. So when I was talking about that need for secondary access paths to a table, this system can deliver consistency with multiple access paths to a very large table. So this is a very similar architecture to other MPP systems, which stands for Massively Parallel Processing Systems. It's actually a very similar architecture to Teradata and NetEaser, ParExcel and Greenplum. But the key element with Postgres Excel is this global transaction manager. Now, the actual code for this has been developed over the last 10 years, and it's been worked on by a number of people. Now, the reason that we've picked it up lately is basically because the direction of that project had stalled and nobody was working on it. So we picked up the code at Postgres Excel 9.2, and we've moved that code forward to the latest version, which at the time was 9.5, and that's now fully released and available. We are just starting work on the Postgres Excel 9.6 version, moving the code forward. So I've got a number of different performance results to share with you. This was a comparison of a 3 terabyte system of Postgres Excel versus Postgres 9.6 with parallel query turned off. Okay, so some might say, wow, that's a really unfair comparison. But what I wanted to do by that is just show the immediate gains that you do get. So that benchmark showed that we were able to make the queries go more than 10 times faster on 50% of the queries. So on a range of typical queries, we've been able to improve performance by more than 10 times. And also that benchmark, though I didn't show you the results for it, but that benchmark did show that we were able to do linear scalability on the database. So increasing the number of nodes decreases the execution time. One thing we also benchmarked was the ability to scale OLTP. So you can actually get higher throughput for transactional systems through this as well. So it's not just decision support or business intelligence, it's actually an OLTP speed up as well. And we did these results on a EC2 cluster, and I'm sort of watching the clock here, so I'll move onwards. But the linear scalability we showed was that based on comparison against the 16-node server, we were able to go twice as fast by moving to 32 nodes and twice as fast again by upgrading to 64 nodes. What we then wanted to do was do a comparison of Excel against 9.6 with parallelism enabled, and what we were able to do there was show that there are still quite considerable performance gains over and above what's in Postgres 9.6. Okay, and the comparison, for example, with an aggregation query is that if you look at the bar on the left is Postgres without parallel query, and then the next two are Postgres 9.6 with first 3 and then 11 workers, and you can see the speed up in performance that you get from that, and then take that in comparison again with a system running Postgres Excel is able to do a much better performance on that. Yep.
How many Excel nodes was that?
That's a great question, which is why we did a apples to apples comparison here of the types of, that's not the right one. What we did was a similar cost comparison. So this is the same number of CPUs, and this is the same dollar cost for both systems to do the comparison. Okay, so we're not really in the department of making stuff up to show to you, but what we have here is some results that are showing you that Postgres Excel still has abilities even beyond 9.6. Okay, so while I'm very happy that we've got parallel query in 9.6, we don't yet have all of the power that we will one day be able to get out of Postgres. And actually it's looking like it's going to take a few more years to get that full power into core Postgres. And we're working on that. Yep.
Couldn't your Excel architecture additionally leverage the parallel query anyways?
Yeah, I mean, what we have at the moment is Postgres 9.5, which does not contain intra-node parallelism, and that's why I have this slide, in fact. So the way that Postgres Excel works at the moment is we use one CPU on each data node, which gives you extra node or massively parallel processing. And what Postgres core is now doing at 9.6 is it's using multiple CPUs, but only on one node. What we're going to get when we move to 9.6 for Excel is the ability to do both. So we'll be able to go considerably faster. Now, one thing that may not be immediately apparent to you is that if you use this parallel technology, although things go faster, they definitely tie up more CPUs, okay? So actually, these things are actually quite resource hungry. And what we want to see over time with business intelligence technology in Postgres is actually to go beyond parallel query and adopt things like Columnstore, where what we're actually doing there is looking at a naturally more efficient mechanism of executing queries rather than a brute force mechanism for executing them. So the number I had in mind was that it will take about 2 to 4 more years worth of releases of Postgres to get the kind of things that we can do with Excel now into core Postgres. Now we are going to be working on that, and the sort of comparison I had really was with streaming replication. It went into 9.0 and we're all really happy when it went in, and then it's taken quite a few more years to add in all of the little gotchas that have emerged from executing it in production. So the reality is that it is going to take some time to get these things in. So Excel is available now for big data. Quite clearly, it does not have the same number of people using Excel as Postgres core. We've obviously got millions of servers in use. The number of people known to be using Excel for reasonable size systems is a couple of dozen at the moment. But as far as I'm aware, the main technology works. We've got relatively few bugs. We've had a few bugs, I'll tell you that, but we've ironed those out over the course of the last year and a half of bringing that to maturity. So what we have now is Postgres Excel 9.5. We released some later versions of that, so we've been keeping up with a regular release cycle. Thomas and Pavan have been starting to look at bringing Postgres Excel up to the 9.6 level so that we can begin to integrate technologies. And so we're just starting to look at the types of things that we're going to do there. But I want to emphasize to you that the objective of that is to get all of this technology into Postgres core. There is no intent to maintain a fork into the longer term, okay? So that was my take on some big data topics. There may be a number of other people that want to discuss other aspects of it. So I'm happy to take questions. So.
Yes, I might just have one question back on one of your early slides when you said that this was similar MPP as things like Teradata, Netezza, et cetera.
Yep.
At our company, we use Teradata currently. We're trying to eventually move away from it, but it suffers quite a bit because of its massive parallelism from skewing if you don't, choose the right key and so forth. How does the Excel architecture pair with Teradata in that aspect?
Perhaps I should say I used to work for Teradata, so I kind of know those systems quite well. The hash distribution mechanism that these systems use do suffer from occasional skewing, but in general it's a kind of relatively good kind of 80-20 way of doing it. It's possible you could work out the perfect distribution of data, but it would take so long to arrange that it wouldn't be as useful. So there's a couple of tricks that you can pull to alleviate some of the problems with skewing, but Teradata's had quite a lot longer to mature than Excel has on that particular point. So if you're looking at serious skew problems, then that's likely to be because you've got a highly normalized schema, and that can cause some problems. So, no magic solutions. Sorry, but hi.
I started testing with it at Enova a couple of weeks ago.
Okay.
I like what I see so far. Pretty cool.
Cool.
There, as I'm sure you know, there's at least a few different distribution options, and I assume that if you do have a case where the data is strangely skewed, the round robin or the random or something aside from the hash might be an option. But I do actually have a question. Have you done any sort of a quasi apples to apples OLTP performance comparison with a single straightforward Postgres instance versus Excel being used? Because I assume there's a great deal more overhead with the coordinators.
Absolutely. I think the thing to understand is that this is scalable, not quick. As soon as you go scalable, then you're going to lose some performance in the manner in which you're doing things. So Excel uses a coordinator node to manage the transaction, which means at the very least getting data back from it means you've got to hop to the coordinator, hop to the data node, and then back. So you've got at least 2 lots of network transit time to get a single request back. So what the objective here is not to maximize the speed of response of any single request, but actually to spread the requests out across multiple nodes and actually to maintain a consistent response time as it scales. So if you have a requirement for extremely fast response time, then that won't scale because you're sort of looking at a data in memory situation. So you've got a trade-off basically to decide how you're going to handle this. And frankly, it causes people a lot of problem because single node Postgres is quite fast and it's very appealing to continue to use that. And at some point, when you take the decision to move to a scalable situation, then your performance per node goes down, and then you need to add a lot more nodes to get the performance back up again. That's what I call the kind of physics of the situation. It's not anything to do with the Excel technology. It's to do with the physics of the way these systems are put together. Yeah.
Right. Okay. Can I ask one more question?
Yeah. Sure. Sorry.
If you are about to get to this, then just let me know. But with the little bit of experience I have, it looks to me like with multiple coordinators, it can behave like a multi-master access point for Right or wrong about that?
Well, Multimaster, yeah, that's a whole different slide deck, well, I mean the developers are sitting right here, so we can ask them. I mean the Postgres BDR is a multi-master technology, and Postgres Excel is really a sharded data technology, and I know that they kind of merge a little bit at the edges, but we need to be clear that I'm not positioning Excel as a multi-master system.
Behave that way, though, if you subject it to that kind of a use case with the global transaction inconsistencies?
I want to run away from that question, yeah, there's some elements of it that would appear to be that way, but I think if you've got that kind of a use case, then you should be looking more at BDR. But again, I do understand there's a merging of requirements. So,
Sure.
but yep.
Can you briefly summarize the capabilities of the visualization tool? I mean, the market for visualization tools is enormous. You look at like Cognos and these guys.
Yeah.
Company spends huge money on that technology, and I hate it because it pulls us away from this type of solution, right?
Yeah.
So, I mean, what's the capability say? Where do you see it going?
So the package, well, so the question is, could you summarize some more the features of the visualization package I showed? So it's a fully open source technology called Orange. It's developed at the University of Ljubljana in Europe. It's not that well known in the US, but it's quite widely used in Europe. It is a very full function package. It does data mining, it does all kinds of visualization. It's been developed over quite a number of years, so it's actually, the version I was showing you there is version 3, which kind of makes it sound like it's only been out a couple of months, but actually that's gone through quite a range of development. So it supports a lot more than just Postgres, but it's a very full technology, and it is fully open source, which is why we're integrating with it as well. So, but I completely agree that there's like about 200 packages, but not all of them have been modified to work so well with Postgres. So, yeah. Oh, sorry. Yep.
Can you talk a little bit of the differences between Postgres Excel and Citus data? Their sharding approach and use cases?
Well, I suppose to be fair, I don't necessarily know Citus well enough to give a completely fair comparison. What I would say is that I know that they have a different data distribution strategy in that they have something that's a bit like partitioning in that they are able to put a section of data on one node with a sort of min and max associated with it, and then another chunk of data on another node, so that it gives you what you might call sort of range distributed data. Now that could be considered to be a better way of doing it depending on the use case that you have. So Excel uses hash distribution strategy as its main mechanism, and that's actually a common thing. All of the systems that I've listed here all provide hash distribution as their default strategy, and so Excel has chosen the same thing. Other than that, I couldn't really comment on what the advantages or disadvantages would be. What I do know is it's not PostgreSQL licensed. So, I did ask Citus Data to release it under the Postgres license so that Second Quadrant would be able to work on it, but that didn't happen, so we haven't got the option. So. Hi.
You mentioned in passing the column storage.
Yes.
And I know Stonebreaker's been doing a lot of math to show how wonderful that's supposed to be, but in a shootout between VoltDB and Postgres, doesn't seem to actually be living up to the truth. Where is that in the
Well, look, the information that we have is that Columnstore provides a very significant throughput and response time advantage because it allows you to take advantage of sort of natural distributions in the data. If you've got a very large data table with lots and lots of columns, the physics of it are simply that if you're accessing a small number of columns, then you don't need to touch all of the other columns. And just simply pure physics, you're moving less data, and so the query goes faster. Okay, so it's real and it's true. The only question is, how the hell do we get it into Postgres, right? So we've been looking at how we do that, and it's more complex than it first appears. Columnstore on its own does very little, and you may have seen something called the Columnstore CStore FDW, and there's some guys in the Netherlands have published a paper showing that actually that doesn't work, because all it does is it only does the Columnstore access. It doesn't have all of the advanced executive functionality required to take full advantage of it. Okay, and so what we need to do to make it work properly for Postgres is there's quite a few changes that we need to make in the executor and in the planner in order to get that to work. So the benefits are real, but it will take us an amount of time to realize those benefits and put that into core. But the good news is we've been working on it for a number of years now. Well, look, it's difficult to kind of sequence all of the projects that people are working on, but we've got quite an amount of research done, and we should be able to get those features into Postgres one day. But you know, it's yeah. So.